Hello and welcome to the IACS Garage. We've been hard at work for the last 8 months developing our Capstone project, which is the custom development of an ECU for the General One Motors LS1. Here we have the GM LS1 engine that we've been working on. We're going to run over a few of the sensors here. We have the mass airflow sensor, we have a throttle position sensor here, and the mass absolute pressure sensor. We have a bank of 4 injectors on this side, the other 4 are here, and here we have 1, 2, 3, 4 coilover packs. They control the ignition to the spark plugs. Over here, we've put together this fuse box to run the engine off the OEM. Because this is an aftermarket installation of this engine, we don't have any of this. This has been pulled off of a 2002 Chevrolet Silverado, and we've had to, you open up the back, we've had to put the wires in there to reroute to the OEM ECU for the LS1 over here. Now you see this big conglomeration of wires here. The reason that we have it all like this is so that we can A, trace where the wires go, and B, take out the unnecessary wires. Okay, so as the signals leave the engine, the OEM needs to monitor these to make the appropriate controls to send the signals back to the injectors, back to the ignition coils to make the engine run properly. Now it takes in the Hall effect sensors from both the crankshaft, the camshaft, as well as the air pressure and flow rate within the intake manifold to calculate how much fuel it needs to send and what time to send the ignition to the cylinder. Because if you don't send the ignition to the cylinder at the right time, you're going to have backfiring, you're not going to have your engine run and whatnot. So the important part of this is that the signals are coming in through the breakout board here. And at this point, it's basically a Y. So the signals come in and they Y out to both ones. And we have jumpers on this breakout board to be able to isolate each of these to either the OEM ECU or to our monitoring system here. Now, what this also allows us to do is hook up an oscilloscope for better diagnosing. We can check the signals coming in, the voltages, the PWM frequencies, and verify that what we're actually getting in physical reality is comparable to what we get on our software. This is our version 2 that's currently running, monitoring the signals, and here we have version 2's PCB. It was nice, it was from San Francisco Bay Area Circuits. And then we have the RUSEFI board. This was the one that it's an open source board developed by a couple masterminds out in the Eastern North America that they put together. They have control signal drivers, they have monitoring signal op amps and whatnot, everything that's necessary to make the whole engine run. And we first developed with this so that we could understand the code and whatnot, and then implement our own system here. The brains behind this this board is the ST Discovery board, an ARM Cortex M4, and this is basically developed off of a C code, but we're running at a higher level just using the Tuner Studio and Developer Console. Here we're going to fire up the engine for you guys to give you a little taste of what we've been developing here. So, ready, set. As you can see, we're running Tuner Studio software on the computer, and we're taking in the signals that the engine is putting out. We're running it through the Revision 2 board here, and as you can see, we have a couple blinking LEDs here to indicate that we're getting the signal for both the crankshaft and the camshaft sensor. The slower blinking one, the slower frequency, is the camshaft, and the higher one that's very hard to distinguish is the 24 times reluctor wheel. As we go, this system is able to monitor at the higher velocities RPMs developed by the LS1 engine.
To configure the board, we used EFI Live's Tuner Studio software. From here we can go through, set all the pinouts for the STM Discovery board, and configure them to exactly what signal we're hoping to get out here. As I run through here relatively quickly, we can see all the different base settings. You can get the engine's firing order, you can get the spark setup, and you can configure it and map it as desired at specific RPMs. Using the dip tray software to design our PCB yielded affordable choice as well as a user-friendly interface. We were able to design our own footprints for the special devices that we had, such as this large header pin here, and design the entire layout on a very higher level schematic view. From here, we were able to develop the subsystems such as the op-amp subsystem, the Hall effect sensor subsystem, and the knock sensor subsystem. Meanwhile, integrating them all back into one and exporting these traces and nets and definitions back into the schematic view. As we came to our first revision, we printed it and got it ordered in. We had a little bit of diagnosing, but overall it was very well done, and we went back to the drawing board and came up with revision 2. From here, we implemented this into the system, and it turned out it worked really well. There was just a small minor change on the configuration, but overall bench testing went very well for this. We tested the system on the Rusafi developer console, which you can see here. I'll give you a brief definition of how this works. Right here you see the gauges and how the overall system's running. In here we have the formula on how we come up with the fuel enrichment process and how much fuel to choose to go in. This is the engine sniffer. You'll see this later on when the engine's running. But this is where you see the crude elements of how the engine speed and ignition and injection all correspond to each other. In here with the messages center is how we can communicate to the ST discovery board. We just type in script with some parameters and it spits out some more script that we can understand and see how the board is configured. Into the bench testing section, we can see all the individual components that are able to be manually output to the certain devices. So in here you see this 8 spark plugs that we were able to control just with a manual push of the button. As we run the engine with the Rusafi developer console, we were able to look back at the engine sniffing page, and we can see on the top here is a 24 times reluctor wheel sending its signal through the Hall effect sensor to the developer console. And with this signal, we're able to determine where top dead center is for cylinder 1 to determine when the first cylinder should be sparking. Thereafter, each of the 7 successive cylinders will just go in their firing order. The firing order is determined by this area here, which is the batched injection. You can see 2 cylinders each are paired up and they get fired at the same time. The fuel injectors, which are just pulse width modulated based on the previous shown formula, are the green signals that you see just previously circled there. Right now we're just revving the engine up just to show how the signals change as the frequencies speed up. Heading over to the Tuner Studio with the engine running, we get a little bit better of a user interface here. We can see the engine speed, coolant temperature, throttle position, just to name a few. As the vehicle revs up, due to the throttle position going up, we can just kind of see real time how it's operating. It's a little friendly, just similar to what you would see in the vehicle. Now if you take a look at the bottom right gauge, you'll be seeing the ignition advance as the RPM goes up. Now this is all due to the mapping that we put in there. Right now it's just mapped to match the OEM ECU's output for ignition advance, but if you're running the racetrack circuit, you're going to have the ability to increase the advance as necessary depending on what types of fuel and how your RPM and what you're expecting to get out of it. The dwell, on the other hand, is hard-coded due to the injector.